We've already talked about discrete joint distributions, so now we're going to talk about continuous joint distributions. So let's start with an example. Recall that for a circular dartboard of radius r, the probability that a dart hits the board within some region D with area A is the area of that region D over the area of the dartboard, pi r squared. And this is assuming that the location of the dart is uniformly distributed across the board. Assuming that the bullseye is located at the origin, we're going to let D be a region that is contained inside the circle, x squared plus y squared is less than or equal to r squared. So how could we find the area of some region D? And what would be the resulting probability density function for the dart location? So if you have a two-dimensional region, we'll call that D, how do you find the area of that region? Well, you might remember from multivariable calculus that if you take the double integral over that region D of just D sub A, then you get the area of the region. Well, what does that imply for the probability that the location of the dart, we'll call that xy, is in that region D? Well, that's the double integral of D sub dA over the area of the total dartboard, which we'll call pi r squared. We could rewrite this as the double integral over the region D of the function 1 over pi r squared, since pi r squared is just a constant, dA. And this looks like the integral of a density function right here. It's now a two-dimensional integral instead of a one-dimensional integral, but it still looks like the integral of a density function. So let's make some definitions. The random variables x and y are jointly continuous if there exists a joint density function, f being a function from R2 to R, such that for all regions D and R2, the probability that the 2 points x and y are in that region D is going to be the double integral over that region D, our density function, f of x, y, dA. Now, if we're going to look at a region D and R2, and we're going to look at the random point xy being uniformly distributed on D, then its joint density function is going to be 1 over the area of that region D, if x and y is in that region D, and 0 otherwise. We saw that with the previous example where the density function for the dartboard was 1 over the area of the dartboard. Note that x and y are only jointly continuous if the joint density function exists. What do I mean by that? Well, unlike discrete random variables, you cannot start with any two continuous random variables and create a density function. You should read more about this in example 6.21. So let's do another example of another joint distribution. So x and y are going to have the joint distribution f of xy equals 2e to the minus x, e to the minus 2y, for x and y between 0 and infinity, and 0 otherwise. We want to find what's the probability that x is less than 1 and y is less than 1. Well, if we have our density function, f of xy, we just need to integrate that over the correct region. So what region would we need to integrate over? Well, in this case, we see that we want x to be less than 1 and y to be less than 1. So we have a square region. X, of course, has to be bigger than 0, bigger than equal to 0. Y has to be bigger than equal to 0. So we want to integrate over this square region. So we're going to do the double integral from 0 to 1, and again from 0 to 1, to describe the region in blue of 2e to the minus x e to the minus 2y dx dy. Now, we can split this integral into two pieces. The integral from 0 to 1 of e to the minus x dx, since that part has nothing to do with y, and then the integral from 0 to 1 of 2e to the minus 2y dy, since that part of the function has nothing to do with x. The antiderivative of e to the minus x is minus e to the minus x, evaluated between 0 and 1. And the antiderivative of e to the minus, or 2e to the minus 2y is minus e to the minus 2y, again evaluated between 0 and 1. So here we get minus e to the minus 1 plus e to the 0, and then minus e to the minus 2 plus e to the 0. We can also write that just as 1 minus e to the minus 1 times 1 minus e to the minus 2. And that's the probability that x is less than 1 and y is less than 1. We can have more interesting probabilities, though. Probabilities like the probability x is less than y. So let's try to draw that region. We're going to look at along the line y equals x. And if x is less than y, then we can shade the region above the line y equals x. That's where x is less than y. So now I need to describe this region as a double integral. We'll let we'll let x vary from 0 to infinity. And that means y starts at the line y equals x and goes to infinity. Here again, we're going to integrate the function 2e to the minus x e to the minus 2y. And now we're going to integrate dy dx. We'll leave the outer integral alone. And I'm going to integrate the 2 times the e to the minus 2y. So leaving the e to the minus x out of it. And I'm going to get minus e to the minus 2y, like we had done before, evaluated between x and infinity. And of course, we still have that integral dx. So now I can integrate from 0 to infinity of e to the minus x times minus e to the minus 2y, evaluated from between infinity and x. That's going to be 0 at infinity plus e to the minus 2x. We can simplify that integral to be the integral from 0 to infinity of e to the minus 3x dx. Now, there are lots of ways that I could do this integral. One way is to write a 1/3 on the outside and then a 3 on the inside. And so I'll get 1/3 times an integral that looks like an exponential distribution with parameter lambda equals 3. And so we know the integral from 0 to infinity of 3e to the minus 3x must be 1. And so the probability that x is less than y using this distribution is 1/3. Finally, let's do the probability that x is less than a. So if we're going to find the probability that x is less than a, let's draw the region out again. Okay, so here's a. If I want x to be less than a, then I'm looking at this region here. So let's see, that looks like the integral from 0 to infinity in y, and the integral from 0 to a in x. And this would be the integral of 2e to the minus x, e to the minus 2y, dx dy. Now, just like that first example, this is going to split up into two integrals, the integral from 0 to a of e to the minus x dx, and the integral from 0 to infinity of 2e to the minus 2y dy. The first integral is minus e to the minus x, evaluated between 0 and a. And the second integral I know is 1 because that is an exponential distribution with parameter lambda equals 2. But I'll do the integral anyway. So I'll get minus e to the minus 2y evaluated between 0 and infinity. The first part of the integral becomes 1 minus e to the minus a. And the second part, if I evaluate it at infinity, I will get 0. And if I evaluated it 0, I will get a 1. So the probability that x is less than a is 1 minus e to the minus a. And that tells me that x is distributed as an exponential function with parameter 1. That's interesting. Okay, let's look at a fact about joint densities. So let f of xy be the joint density of x and y, and then the marginal densities of x and y are the integrals of f of xy over all possible y values, and that will give us the marginal function for x, marginal distribution, or density, of x. And then the marginal density of y is the integral from minus infinity to infinity of f of xy dx. So essentially, the marginal densities are where we integrate out all the possible y's to get the marginal density of x, or integrate out all the possible x's to get the marginal density of y. Now that we know something about marginal densities, we should figure out how to compute expected values with jointly continuous random variables. So we're going to let g be a function from R2 to R so that it's a function of x and y, and x and y be jointly continuous random variables with a density f of xy. So what is the expected value of g of xy? Well, it's the double integral from minus infinity to infinity. Minus infinity to infinity. So that's integrating over all possible values, x and y, of the function g of xy times the density f of xy. And we can write dy dx or dx dy. And this is the expected value provided the integral is well defined. Okay, so let's go back to our example where our joint distribution is f of xy equals 2e to the minus x e to the minus 2y. And let's find the expected value of x times y. So the expected value of xy is the integral from 0 to infinity, so integrating over all x's and all y's, of x times y times the density 2e to the minus x e to the minus 2y dx dy. And like some of our previous examples, we can actually split this one up into two integrals. The integral from 0 to infinity of x e to the minus x dx, and the integral from 0 to infinity of y times 2e to the minus 2y dy. Now I'm going to notice something interesting here. This looks like the mean of an exponential distribution with parameter 1. And this integral here looks like the mean of an exponential distribution with parameter 2. So we already know the means of the exponential distributions. They're 1 over lambda. So we might as well write this or solve this integral very quickly as 1 over 1 times 1 over 2. And then, of course, equals 1/2. You could get the same answer by integrating by parts for both of the integrals, but I think recognizing these as exponential distributions is much faster. So this concludes our lesson about joint distributions for continuous random variables. And we have these examples of finding probabilities using double integrals, as well as finding expectations using double integrals.